Hey, welcome back. Today we're taking a look at electronegativity and ionic radius. So, as usual, this chapter has a lot of key terms, and here are the last two for you to be aware of. Electronegativity is a measure of the ability of an atom to attract electrons in a chemical bond. And ionic radius is the measured size of the ion formed when an atom loses an electron, and that'd be a cation, or when it gains an electron, and that'd be an anion. So real quick, electronegativity is how much an electron pulls on electrons in a chemical bond. So it's like this cartoon here, fluorine. You can see fluorine here. He is the most electronegative atom, darkest purple, most electronegative. If he's in a tug of war over an electron, so he's bonded to hydrogen here. If he's in a tug of war, hydrogen only has 2.2, so that's not very high. Now, the lowest on the periodic table is francium, down here with a 0.7. That's the lowest electronegativity. But a difference of, almost 4 of fluorine and 2.2 of hydrogen is a pretty big difference on the periodic table. So fluorine's going to pull that electron a lot closer to himself, even though they're sharing it, even though it's bonded. It's going to pull that electron a lot closer to himself because he has the greater electronegativity. So that's what electronegativity is. The greater you have, the more you pull on a shared electron in a bond. Generally, the electronegativity increases as you move across a period, so it's getting bigger. The noble gases being the exception, they don't bond, so they're not listed here. They don't really make bonds, so how can they share electrons in a bond? And electronegativity generally decreases as you go down a group. So you can see that's a pretty general trend there. It's getting smaller as you go down, larger as you go left to right. All right, we'll come back and we'll work a lot more with electronegativity in our next unit. Just wanted to introduce it to you now, so it's not foreign when we get there. But most of the rest of what we're going to talk about are ionic radius. So quick recap, ions are formed when an atom gains or loses an electron. So here we have that. If an atom loses an electron, it's going to have a positive charge. It's going to have more protons than electrons. Electrons are negatively charged. Protons are positively charged. So if you have more positives than negatives, you'll end up with a positive charge. We call these cations. On the other hand, if you gain an electron, same is true. Electrons are negatively charged, so if an atom gains an electron, it now has more electrons than protons. That's more negative charges than positive charges. So you're now going to have a negatively charged ion that we call an anion. So atoms tend to gain or lose electrons in order to fill their valence shell. That would be P6. So sodium, for example, he'll give up an electron so we can get back to that octet, which is our P6. He has S2, P6, octet. 6 electrons in the P, 2 in the S. That's a full octet. That's 8 electrons. And there he goes. He's got that full shell. That's why he gave up or lost that electron. Nonmetals usually gain electrons so that they can complete their set. So here's chlorine, the atom. And you can notice he's 1 electron away from having that P6, that full octet on the outside. So he gains an electron, and now he's got all 8 electrons on his outer shell. That's a full valence shell. He did it a different way than a metal would, sodium for instance, but he got to his full octet, and that's why he gained an electron. He formed an anion. So that brings us to oxidation states. These are the charges that atoms are likely to form when they form an ion. Now remember from earlier in this chapter, elements in the same group have the same number of valence electrons. So everybody in the alkali metal family, it's group 1 here, they'll have 1 valence electron. Guess what? Every single one of them is going to lose an electron, just 1, to get back to P6. So they're all going to have a positive 1 charge. The alkaline earth family, so they're group 2 here, they all have 2 valence electrons. They're all going to go back 2. They're going to give up 2 electrons to get back to that P6. Halogens, so coming over here on the other side of the periodic table, halogens are all going to gain 1 electron. So they're all going to form a -1 charge over in this family in order to reach that full octet. Alright, so that brings us to our ionic radius. So similar to atomic radius, we talked about that at the beginning of this chapter, the ionic radius is a measure of the size of an ion. So how big are those ions? Well, it depends what type of ion it is. Cations tend to be smaller than the atom that formed them. So, for instance, here's a lithium atom. It's a metal. He's going to lose an electron and form a cation, and that cation is smaller than the atom that formed it. So we know it's a cation because it's got that positive charge. So it lets us know, and then it's much smaller than the size of the atom that formed it. Anions tend to get bigger when they form. So here's chlorine, the atom, and here's chloride, the ion. Again, we know that because of that negative charge. And notice chloride is significantly larger than chlorine. So anions get bigger. With cations, there are 2 reasons that they get smaller. First, and this is probably the biggest and the most evident, is that when they're giving up an electron, so here's the electron, here's sodium, here's only a valence electron, he gives that up and he goes down to a full octet at the energy level below. But guess what? That means he erased this whole energy level. It's gone. So he's much smaller now. You can see this is his size here now versus this is what his size used to be. So showing us what it is now versus what it used to be. So that's the first and most evident and probably the biggest reason why cations get smaller. But also take a look at the ratio. 11 protons. That doesn't change. Here we have a 1-to-1 ratio. 11 protons, 11 electrons. Here we have 11 protons and 10 electrons. These protons are now able to pull on those electrons even tighter. It was a 1-to-1 ratio, now it's greater than 1-to-1. So the force of the nucleus is stronger on each individual electron than what it used to be, and so they're getting pulled in even tighter. Anions get larger, and this is also for 2 reasons. First of all, pretty much the opposite of what we just talked about. The nuclear charge on every electron is actually now less than what it was. Still 9 protons, fluorine, the atom, fluoride, the ion. The protons don't change, but the number of electrons do. In the atom, we have a 1-to-1 ratio. So that nucleus is able to pull 1-to-1 on every electron. But in the ion, fluoride, it's now a less than 1-to-1. It's a 9/10 of 1. So that nucleus is only pulling on those electrons about 90% of what it was. So for that reason, it's not able to hold on to them and pull them in as tightly. And that's why we get a little bit larger atom. Those electrons are getting a little bit further away. The nucleus just can't hold on to them. The second reason is the electrons themselves. There's now more electrons in the same area. They don't want to be close to each other. They're all negatively charged. They need more room. So they spread out a little bit, and that makes them a little bit larger of an ion. I always really like this chart here. There's a lot going on, so you got to take a minute and think about what you're looking at. They show us here 3 types of atoms. We have metals. They're in blue. So here's the size of the metal. The blue circle, that's its radius. We have the semimetals, or metalloids. They're along the stair-step line. They're the gold atoms. And then we have the nonmetals, which are these brown atoms. So we've got all that listed here. And see that general trend from blue to yellow to brown? Our atomic radius is getting smaller, 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 smaller. But when you take a look at the ions, so all of the ions, whether it's a metal ion, a cation, or an anion, or a nonmetal ion, they're all in this black shade. So you see your metals, all of their ions get smaller. Here's potassium, the atom, in blue. Here's potassium, the ion, in black. It got smaller. Here's iron, the atom, in blue. Here's iron, the ion, in black. It got smaller. We jump over here to the nonmetals, and we see the opposite is true. Again, the brown represents the atom. Here's phosphorus, the atom. And the black represents the ion. Here's phosphide, the ion. So that got bigger. Here's chlorine, the atom, just brown. Here's chloride, the ion, black. It got a lot bigger. So again, I always like this chart. A lot going on, but when you slow down and take a look at it, you can see all the trends of atomic size, atomic radius, and ionic radius, ionic size. You can see them all as you move across and up and down the periodic table. All right, that's a wrap for this unit. So finish up that homework, and we'll get going on our next unit, bonding, later this week.